Assalamualaikum and a very good day to Dr. Sharul and Dr. Aidil. I am Muhammad Ashraf bin Anwar. Would like to present my FYP II presentation entitled Parametric Study of Getting System Design for Magnesium Casting of Test Piece under supervision from IR Dr. Daniel Ibrahim and co-supervised by the Associate Prof. Dr. Yutas Nami from Tokai University. So a little bit introduction about this study. This study is focusing on the casting of test piece. A test piece is a tool to measure and detecting 90-degree angle product. Moving on to research objective of this study. So the research objective of this study is to complete computational fluid dynamics simulation with alteration of parametric level and then collect data. Then identify the effect on temperature and velocity distribution of molten metal based on modification of parametric value. And lastly, comparison between the optimized design with modified parametric value and sample mold. A study is conducted to analyze the porosity formation inside the test piece. So this figure 3 here shows the result from the result of X-ray CT scan on the test piece. So the study found out that most porosity found on the thickest spot of the test piece. Next, a study also is conducted by Lee, Beck, and Han to show comparison between the conventional mold and the vacuum system installed to the conventional mold in figure 5D here. So the result from the study shows that 98.75% lesser volume fraction of air is found at the red spot here, to indicate that the vacuum system model shows lesser porosity. So the methodology that is used to conduct this study is by selecting the parameters for boundary condition, which is velocity of the molten metal and the operating condition of at the event. So the inlet velocity of molten metal is selected ranging from 1.5 meter per second until 3.0 meter per second, as we can see here from the table. And the operating condition at the event is ranging from -10 Pascal until 10,000 Pascal. So a total of 36 simulation is done in order to get a set of data consisting each of the parameter used. The result. So the graph here in figure 6 and 7 shows a pattern of graph shows that the meshing for the simulation is in good quality. So good quality of meshing could reduce calculation errors, allow better convergence, and assure high accuracy of the numerical solution from the simulation. So all of the data collected from the completed CFD simulation is plotted into this 3D graph. This graph shows how the modification of parametric value could lead to different outcome, which is the pressure at the critical point of the molten metal. I will later show it the critical point in the slides. So from the graph, you can say that as the inlet velocity increase, the pressure created at the critical point is also increasing. For all the operating condition. So high pressure at critical point is more desirable as it helps dispersing away the air bubble out from the die cavity. So this is where the critical point is located, at the very middle of the thickest spot of the test piece. So why we choose at the middle of it? Because from the previous literature review that I mentioned, it is found out that most porosity is formed at that particular point. So next, the result showing the effect of modification of inlet velocity towards the velocity distribution of molten metal. As we can see here, as the higher velocity of molten metal, the more turbulent flow of the molten metal. As we can see here, the flow of molten metal in 5C causing the turbulence flow, causing a space in the die cavity is not fully occupied. The spaces that not fully occupied will then produce porosity. Next, the effect of modification of inlet velocity towards the inner temperature distribution of the molten metal at the test piece. So as we can see here, as the increasing inlet velocity, a more unbalanced temperature distribution is found on the cross-sectional area of the critical point. It is not a good thing, as the high temperature region will solidify later than the other region. The solidified molten metal might trap the air bubbles, thus insufficient molten metal to completely fill the section. The different cooling rate can cause shrinkage to cast product and increase porosity defect due to ununiform solidification. Next is the surface temperature distribution. This one is also same as the inner temperature distribution. As the inlet velocity increase, the more unstable distribution of temperature. Next figure is showing the effect of modification of operating condition towards velocity distribution of molten metal and the temperature distribution. So the result shows that no significant changes is created by changing the operating condition for velocity distribution, and same goes to the temperature distribution. No significant changes is noticed from the modification of operating condition, as you can see here from figure 13a and figure 13b. No significant changes is found. But then the numerical result for inlet velocity 2.0 meter per second is shown from the table here. So it was found out that when operating condition 10 Pascal, the pressure at critical point is the highest, which is more preferable, because the more pressure at the critical point, the more it helps in dispersing away the air bubble trap. Next is the comparison between the machine parametric value provided by Kyokuto diecast, which is an inlet velocity of 2 meters per second for sample mold, and the modified parametric value towards the optimized mold design. So as we can see here, the velocity distribution inside the sample mold is formation of vortex. You can see here the formation of vortex. So this formation of vortex will produce air porosity. But then if we see here in figure 14b, we can say that by using same inlet velocity provided by Kyokuto diecast, but using operating condition of 10,000 Pascal, we can say that the molten metal is balancedly distributed inside the die cavity, which fully occupied the die cavity. Next is the comparison for temperature distribution for both mold. So we can see here that sample mold has higher incline difference of temperature compared to the figure 15b here. So higher difference in the highest and lowest temperature region could lead more ununiform solidification of molten metal, which is not a good thing because it may cause porosity. So this is maybe why there is more porosity found on the thicker spot of the test piece, as mentioned before on the literature review for the sample mold. As the conclusion for this study is the parameter that could cause porosity in die casting product is the inlet velocity of molten metal and the operating condition at the event. The increasing inlet velocity will cause more turbulence and unbalanced temperature distribution, which cause more porosity, while the increasing pressure of operating condition causing no significant changes towards the velocity and temperature distribution of the molten metal, but can cause changes of pressure at the critical point. Lastly, the amount of porosity is reduced by applying the modified parametric value into the optimized design. So the recommendation is increasing the parametric range during simulation to increase the possibilities to detect defect source. Next is analyzing process. Should consider other parameters such as the cooling system of the mold and the different phases of plunger speed. And lastly, recommendation is More reliable software such as JSCAS, Modfrontier, and Magmasoft needs to be utilized by students to get better results. That's all. Thank you very much.